right, so here we go. I'm starting the recording. This is our Design 330 lecture on Tuesday, April 27th at 10 o'clock, and we're in a live meet. And our subject today is the MEP Plumbing. You'll see from our calendar that that's what's up this week, MEP Plumbing. This is the last of the new material for the semester. The rest of the semester will be putting things all together. Next week, let's see if I can click on the right one here. Hold on a sec. There we go. Next week, we'll be putting all of the sheets together with a cover page and a few sign-off sheets into one full MEP set. And it's a little bit light. The MEP set that I worked with for the Academy of Sciences in Golden Gate Park had about 200 sheets in it, and that was a preliminary set. So ours is a pretty small set, but it's a fairly reasonable complete set, and we'll work on that next week. And then the following week is just clean up and get ready for your final submittals, which is just going back and making sure that everything looks good. So that's what we've got. That's what we've got cooking this week. Again, is MEP Plumbing Sheets. Let's see what's on the to-do list. There is a playlist of tutorials that I think will get you through everything. I'm not going to really do all of the modeling exactly unless I have questions on it. I think the tutorials cover pretty closely what you're going to need to do. There is a submittal template for you available that we'll look at. There is a sanitary drain system image and description. So last week, some people didn't really quite do what the requirement was for, I'll show you, your submittal. This second page here, last week was a visualization of electrical system, and I was looking for how do you get from power generation all the way to the receptacle. And so that's what I was looking for here. This week, I'm looking for a visual of the sanitary drain system and an explanation of it. So I've given it to you. I gave it to you last time too. Here's the visual right here. I'm going to open it up in a new tab. There it is. Houses and buildings have sanitary drain that goes down and collects in a main sanitary drain line, and it goes to what's called a pumping station. And that pumping station adds pressure so they can put it into the gigantic pipes that lead to, these are like 60-inch pipes, up to 60-inch pipes that go to the wastewater treatment plant, SAC Regional Wastewater Treatment Plant. And then it goes through all the processes there, and a small amount of it goes out to Elk Grove as gray water for their park system. And the majority of it goes back into the Sacramento River. And they have all sorts of treatment requirements and things like that to make sure that they're putting in good water. And so that's what we want to see in that spot so that you understand what a drain system is. The reason for that is we are not doing a drain system this semester. We've done it in the past, but with the remote operations, things just don't quite move as fast, and we're going to focus on the cold water system. And then I've given you some plumbing sheets that will need to get done. So there's a bunch of sheets here, and that's what a system looks like. So that's what I've given to you. You've got one more set of details, one more set of mechanical, electrical, and plumbing details, and then that's it. Important files are in the same place. There is a discussion board posting, and I just need you to read this through. We'll go over it, but this is about a very important calculated value called residual pressure. And that calculation tells you whether you're going to be able to occupy your building or not once it's built. So it's a very, very important one. And so this is a little bit of description of it, and just need you to make a quick video about how it's done. I'm going to suggest you try Vimeo, and I'm going to try one on Vimeo to show you if you don't already have a way to do it. If you don't have PowerPoint or OBS or Zoom, Vimeo is a Google Chrome extension. So that if you're on a Windows machine using Google Chrome, you can use it. If you're on a Chromebook, you can use it. It's pretty nice. They do take some data for you, but it's not from you, but it's not too bad. You do have to make a free account. You do not need to make a reply this week. Okay, so that's what's coming in. And of course, there's submit your work onto Canvas as we always do. So that's what's up for the week. Today, I'm going to just talk about some terms here. Cold water supply, hot water supply, sanitary drain, vent, hydronic. Those are important because you will see when you put some plumbing in. Let me go to a plumbing floor plan here. And if I say I want to put in a piece of pipe, which is under systems, click and put in a piece of pipe, it doesn't really come up right away, but down here it'll ask you for what kind of pipe are you putting in. Is it a domestic cold water? Is it hot water? There's all these different things. Is it fire protection, sanitary drain? So these are important because it helps you organize your piping so that it hooks to your fixtures appropriately. So if I try to hook this cold water pipe to a hot water faucet, it'll give me an error. And that's appropriate. That would be what's called the cross connection. So you have to sort of know what your water is going to do when you hook it up. So let's talk about those a little bit. Cold water supply is also called domestic. It's also called potable, and it's also called drinking water. So I'm most familiar with calling it CWS, cold water supply, but you'll see that Revit calls it domestic cold water. So you could call it DCW if you wanted to hang with exactly what they call it. And you can imagine domestic is stuff that people are going to use. Okay, so domestic supply in general will supply drinking fountains, sinks where you might fill a glass with water. Often it will supply your lavatories and your water closets, your toilets and your showers. Although if you've got a gray water system, it's really, really economical and conservation wise, it's really good if you can supply your toilet and some of your wash down and your irrigation with gray water instead of domestic water. Domestic water has to be treated to a higher degree of safety. You have to be able to ingest it. And it has to have, there's contaminants. That's things in your water that make you sick. And there's pollutants. That's things in your water that just look ugly, but don't make you sick. So a little bit of extra salt or dirt or maybe calcium in your water would be a pollutant. And there's limits on that, which can vary and they can be fairly high because they don't make you sick. And then there's contaminants, giardia, viruses, bacteria, food stuff, waste, personal waste. Those can really make you sick, or heavy metals, things like that. And those are much more strongly regulated even than pollutants. Um, and so domestic cold water meets a high level of requirements. And so if you're watering your lawn with domestic water, you're really doing a lot of water treatment and getting really good water just to put on your lawn, which doesn't care whether it's got a little bacteria or not, or even a little barium or a little salt or a little calcium or even some dirt. They call that suspended solids. So domestic cold water, though, you'll see here, that's our blue line in Revit, is going to feed our lavatories. In this case, we're feeding our, our water closets because we don't have a gray water system. It's feeding our hoses that are going to fill up our tub here, our pool. We could really use a gray water system in this operation. Now over here, as we feed, the reason I put this on a hose is there's a water softener over here, and there might even be something called a reverse osmosis filter or a still that really makes my water super, super pure, since this is a chemistry lab area. When I worked in a chemistry lab, we had all sorts of things. We had a still, we had distilled water, we had purified water, which was run through a filter. We had reverse osmosis water, which is another type of filter that's very, very fine. We had a number of treated waters that had different chemicals in it on purpose. We had water that was UV. So depending on, and I worked in a wastewater lab, by the way. So all of the things that we would be doing in this little area, testing water, that's what I did for about 3 or 4 years while I was in college. I was a sewage treatment plant grunt. I collected sewage, I tested sewage, and I treated sewage. And I swore I would not do that for my profession. And then a few years later, I worked for a wastewater pump company. And I collected sewage, and I pumped sewage, and I treated sewage. So best laid plans sometimes go awry. And actually, it was probably the best job I've ever had. That company was so well run. It ran so well. So I truly, truly enjoyed it. It was called Wemco Pumps. And then they moved to Utah when they got bought by another company, and I decided not to go. So anyway, domestic cold water, that's what we're using. Now, the next one in the list is hot water supply, domestic potable drinking water for hot water. And you'll see on ours, we don't have hot water, right? You're not seeing it. I don't have any hot water lines, even though I might need hot water here at the lavatories. I almost for sure will. I probably need some hot water over here. So why don't I have hot water? Well, I didn't put them in just because we don't really have time, but a very common way when you need small amounts of hot water on demand, just when I open it, and I'm not going to use a lot, is to use what's called a point of use, POU, and you'll see them all over the place at ARC and most most restrooms. It's just a little tiny hot water heater that heats it up instantly as the cold water passes through. So we would just take some of our cold water, divert it into that little piece of equipment, and put it into the hot water tap of the sink. Now that's got some really good stuff behind it. So hot water has to be heated to at least 125 to 135 degrees to kill Legionnaire's disease, which is one of the main causes of illness that's waterborne, that just happens. It just happens. So your water heater at home should be set for 125 to 130 degrees. Well, that will scald you. That's hotter than most people. I mean, there's a few people that can stick their hand under there and don't seem to be affected. But that's hot. 110 degrees is considered good hot water to wash your hands in, up to 120 degrees. And so you need that hot water super hot somewhere. So if my hot water heater is sitting here, I've got to get it up to 135 or 140 by the time it gets over to here to mix with my cold water. So it's not as efficient in general to have a hot water heater and then put your little point of use on. However, point of use can really pull too much energy all at once for your electrical. So what some places do is they put a 40 or a 50 or a 60 degree water tank. It's not really hot, but it doesn't lose a lot of energy through um, convection to the air. And then this only has to increase 60 to 70 degrees instead of, if it's really cold outside, maybe even 90 to 100 degrees. So hot water for us is ignored, but usually it would be in there. And if I wanted to put a hot water pipe in, you'll see it's red. That's really cool. Cold blue, red hot in Revit. Okay, so that's kind of neat. That's hot water supply. The next one to talk about is sanitary drain. That's your sewage. And we're not going over that, but you would see that a sanitary drain line usually goes deep. It's gravity fed. So gravity has to pull it down. So it has to be at a slope or the sewage will pool. And you don't want that. That causes all sorts of illness problems, public health problems. So you will have, excuse me, drain lines that are usually 2, 3, 4, 6 inches in diameter, and they'll slope downwards. And by the time it gets out to the street, you'll usually be at somewhere 6 to 10 feet below the street level. That's how low they make it. And then it just keeps going down, down, down for miles until it gets to one of those pumping plants that we showed. And then it'll pump it up to a higher level, and then it'll feed down, 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 down until it gets to another pumping station, and then it'll pump it up and down, 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 down. So if you go to Sac Regional, where it finally is, it's got to get, it can't be 30 or 40 or 50 feet under. Actually, it is. It's about 35 feet underground, but it's a big 60-inch. I think they might even have a 100-inch line, and the pumps are ginormous, and they do about 60,000 gallons a minute of sewage for each pump, and they've got many of those pumps. It's really cool. If you want to take a cool field trip, just go there sometime. Sign up for one of their public tours. And it is amazing. And you'll see some Wemco pumps that I helped design and install when you get there. Okay, so that's our next one, sanitary drain. And that's really, everything has a drain. You have to get rid of the water somehow. And they'll all go to the same place in this type of a building. But sometime water from a toilet is considered black water because it is contaminated. So is water from a kitchen sink or somewhere where chemicals can be poured down. That's considered contaminated. But where you just wash your hands or take a shower is considered polluted. Okay, and so that could be gray water. We don't have a gray water line. We're not showing the drain lines. In most buildings, all of your lines run to the same spot, and they're just sanitary drain. and they don't make a difference between black water and gray water. Okay. And so these would all just have a drain hooked up to, you can see it there. There's a drain line right there. Straight pipe, drain line. And you would just hook up to the drain with sanitary drain. And it's always got a slope. It has to slope down. Okay. That's all we're really going to say about it in this case. I just want you to know that it does exist. And then there's vents. Drain lines and many pieces of equipment have gases. Excuse me. I'm going to get a quick drink here. There's gases that come off of them. Sewage, in particular, has gases. And so you'll see a trap that's got some water in it that keeps the gases from coming into your house. But if you just let the gases build up, there will be enough pressure that your water will never drain. So there's usually a vent somewhere that goes up through the roof and into the atmosphere so that your gases can escape. It also keeps gravity flow going so that you can't just get a little trap of a pressure trap there. Okay, so there's vent, and we're not talking about the vent either. And then the last thing is any water that goes to a heating or cooling system is called hydronic. And so you can see hydronic lines too. And you'll see all of those when you decide to put in a piece of pipe. There's sanitary, vent, hydronic, supply, hydronic return. We didn't talk about fire protection. This place would need a fire protection system too. Fire protection is very cool. Because I was a pump and valve person, my pumps and valves got used on all types of systems, and I got to do a bunch with fire protection systems. I was actually a member of NFPA, National Fire Protection Association, and got to learn a lot about fire protection systems. Excuse me. And many of them are done very, very poorly. So that's really the main thing for today. Let's see what else I wanted to go. Here's your modeling playlist. So the order that you do things, of course, you set up your view. You put trunk lines in. Let's see a trunk line. Come on. This big line is a trunk line. It's the main line that comes in from the outside, and it's big like the trunk of a tree, and it goes like the main backbone through the system. Okay. And then there are branches that are smaller, and then there's the feeds. Okay. So trunk, branch, feed line. Usually you really talk about the trunks and the branches when you're doing all of your estimating. So that's why I said anything over 5 feet long we'll consider as being a reasonable thing. So once you've got your trunk lines, then you place your fixtures. Those are the things that take water. Toilets, lavatories. And then we put in a thing called a hose bib. It's just a little valve that you can turn on and off, and you can hook a hose to it or another piece of pipe or something. And it's just a place where you can connect up and get water. And we put those all over the place. If you look at those, they're all of these are hose bibs. Here's one to go to a connection in the coffee room. Here's a bunch for the pool. Here's one over here to feed anything that might be needed. Here's one over here to feed any of the chemical stuff. Okay, so there's hose bibs in there. And then there's fixtures. There's toilets. Okay, and lavatories. And then, of course, I didn't hook up to the to the hydronic. You could hook up to the hydronic if you wanted to. You could put a hook into the water softener too if you wanted to. But in general, somebody would put a little manifold off of that hose bib and then hook into it. Okay, so you put in your trunk lines, and that's usually big, and then you place your fixtures, and then you sort of look at those fixtures and figure out how much water you're going to need in each branch and sort of estimate how big it's going to be. And then you connect to your fixtures. Once you've got that, you'll annotate, do your schedules, and then of course you need to do your discussion board, which is residual pressure. So I'll talk about residual pressure just a little bit using this. Okay, if I've got 60 psi being provided as water pressure, okay, I've got 60 psi, maybe 70, 80, 90, 30. The water purveyor, your water company, has to ensure that you have a certain amount of pressure at the beginning of your building. But as water flows through pipes, it loses pressure. The faster it flows through the pipe, the more pressure it loses. Okay? And the farther it goes, the more pressure it loses. So speed and length determine how much it's going to lose. So if I want a certain pressure at my hose bib, I have to make sure that I've got enough pressure at the start, and that as the water flows through the piping, that I still have enough pressure when I'm done. And that pressure is called the residual pressure. Residual means how much is left. So how much pressure is left by the time water gets here? Well, that's kind of a hard one to calculate because there's so many things involved. Did this flush? Did this turn on? Did this turn on? Did that turn on? All of those, when they turn on, they have an effect on the pressure in the pipe. So it's a pretty tough calculation to figure out. Fortunately, Revit does it for you. It figures out something called the critical path. If everything were to open up at one time, there's one place where my pressure loss is the most, and that's called the critical path. And it might be going through here and all the way down to here, or it might be coming through here and over to this sink, or it might be coming all the way over to here. I don't know. But Revit does that calculation for you. And it's called the critical path. And when you look at that critical path analysis, you can find it. So I'm going to go look at, I'm going to do an analysis right now. So I'm going to go to Analyze, and I'm going to turn on my system viewer. Sorry, I need my system viewer to be on. I'm going to look at my system browser, piping, and I'm going to go to Analyze, and I'm going to do a pipe pressure loss report. Click. And I'll say, which one do you want to do? Well, I've only got one. I've got one cold water system. So I'll run it. And there it goes. Bink. And I have to save it somewhere. So I could go back and just open this up, but I'm showing you how to do it. Yeah, I'll replace it. It's the same one. And it's going to come up. There it is. And oh, I hate this stupid Internet Explorer thing. Always ask me what I don't want to do. Okay, and there's tons of information here. Every single pipe, what the flow in it is, what the size is, what section it is, what velocity I've got, what's my velocity pressure, how much pressure how much friction there is per 100 feet, and how, oh my gosh, section pressure loss. I've got all sorts of things in here, and you can imagine putting that all together and figuring out the flow in the worst one would be hard, but there it is. Down at the bottom, there's something called critical path. And it says my total pressure loss is 35.8. So in the worst case, I'm going to lose 35.48 psi. Now, some of these numbers might look a little weird, like really 15 gallons a minute? That's because there's a flush valve. Flush valves are so fast and so hard on a system that they totally increase the flow rate far more than you would think. So you could, if these, but flush valves also use very, very little amount of water to flush big chunks. So flush valves are really good in one way, but they're really hard in your system on another way. They're really good for saving water, but they're really hard on your pressure loss. So we just need to make sure that we've sized things right. So I'm going to lose 35.48. If I started with 60 and I lose minus 35.48, I will always have at least 24.52 psi at my hose bib or at my piece of equipment. And the requirement is that I have 22.5. So I'm okay. If my requirement, if I fell below 22.5, if I lost too much pressure, I'd have to do something. Shorten my pipes. Put in something that doesn't lose so much pressure. Put in a bigger pipe so that it doesn't lose so much pressure. There's all sorts of things I could do to fix that. You don't have to worry about that. You just have to know that you're going to take your inlet pressure, which I've told you is 60, and subtract whatever you get from your model as the total pressure. And if yours ends up being less than 22.5, you just have to report that. You do not have to fix it. You're not the plumbing engineer. You're just a modeler right now that's giving information to your plumbing engineer. Okay, so you're gonna go through that and tell me how you did it. Right? You're gonna say I got 60. I found my friction loss from my Revit calculation. It was when I subtract it, I get something, and it is at least 22.5, or I have a problem because it's less than 22.5. Okay, so there we go. That's your lecture for this week. The modeling has all been laid out for you in the playlist. So I'm just going to let you watch those, and then if you have a question, email me or come to the lab and I will do the demonstration for you during lab. If you go, I tried to do the trunk lines and something wasn't working. And you can send me your model and I'll look it over and see what we can do to fix that. But you got to give it a try first, all right? And go in the order that it shows up in the playlist. I think I have the order correct in the playlist. If not, go by this order right here. Okay, any questions at this point? All right, then I'm going to go ahead and stop the recording